Here's a quick video on how to read Python data in from Scopy so that you can calculate the full width, half maximum, and RMS. I won't go over how we got to this screen, but the time base in this case, to be similar, what we're doing in LT-SPICE needs to be about 50 milliseconds. And you can see the RMS value is coming out there anyway. All right, so really, I just have to come back, click this button, and click export. And really, you're going to have to use the same file names I use for everything to work seamlessly. So I'm calling everything full width, half max, and it makes this comma separated value. Now, you could use Python to do what I'm about to do, but I just don't have the time to figure it out. So you have to process it a little bit. All right, so wherever you've saved it, and you should keep it in your summer bridge. All right, double click on it to open it. You need to delete these things or Python will kind of choke. All right, and Python doesn't need the sample. All right, you need to change these so that you don't have to fiddle with the variables. So, but it's got to be exactly named, case sensitive, time, noise, and vout. That has to be exactly the same, otherwise it won't work. I mean, you can always fix it, but so I just want to save it at CSV. There it is. All right. Now this Python file, there's the link is in the lab manual. All right. Instead of reading in a wave, we're using a Panda data frame to read in the data, right? And you just, if you don't, if you use different files names, you just have to change it there, right? And then we're calling time data.time, and that's why these names have to be exact, right? And when you run it, it gives you the names you actually put in there when you run it. So if you've made a mistake and it can't find something, chances are you've mislabeled this. It tells you what it is, and then you can change the code here if you want. So time is time, scaled noise is from the noise, and then this X data is the vout data. You need to calculate the sampling frequency, and you just take two adjacent times, subtract them, and do 1 over. All right. Well, once you've got that, this calculation is the same, and then it goes through and will plot the power spectrum and plot the Lorentzian fit to that. So almost everything is the same. So you just have to run it. And we get RMS of 0.27, which was what we were measuring in Scopy. We have a full width half maximum of 98. Now here's the thing, I did this before, right, and I got a full width half maximum of 78. And that's because one, it's real data, there's real noise, even though the data is coming from a fixed source, meaning it'll give you the same noise every time. Little bluegrass there to make us all happy. So don't worry if when you run it, it'll come out differently. All right, now what we can try to do is, where is Scopy? Is we can do a longer time frame, right? Do 100. Oop. Just takes a while for the buffer to fill up, and we can so that's just more data. right? We'll export that. Right? If you run it, let's actually just run it as is. It should choke. Right? Things are wrong. Right? That meant I have to go back. And again, this is a perfect thing for Python to do. Okay, that looks good. I did save it. So last time we were getting 98. Let's run it again. And we're getting 89. All right. And I think actually doing it for longer didn't actually help, because really this repeats every second. All right. This, we only have enough noise data for 1 second, and so we're going over 1 second. I thought it might be better, but it seemed this was just as good. All right, so don't sweat it. It's that every time you do it, you get a slightly different value. And the thing is that full width half maximum, that Kramer's rate, it is just an average. The stochastic resonance will work. It says it's got to be of the same order of magnitude, but I've seen it work at even higher and lower frequencies than that. All right, that should get you your full width half max data, which I said I wasn't going to do, but that's okay.